And hello, everyone. We are live to this very special stream together with engineer Calum Douglas, of course, the author of The Secret Horsepower Race. And I'm very happy that my camera is picking this up. And hello, everyone. Of the filter. Are live to this very I'm getting my own special echo here. So together with turn this off. And there we go. Can everybody hear us? Calum, hello.
Hello.
How are we on this Saturday?
Looking forward to talking to so many people.
Yes, it's going to be absolutely fantastic. We have a good lineup of questions already from our Patreons and channel members, and I think we're going to have a fantastic discussion here on engines, of course. And then we're also always putting it up on for the stream to submit your own questions. You can already go ahead and submit your questions. Coconut there, our fantastic volunteer moderator, is going to collect them as well and let me know. But first we're going to go through the Patreon and channel questions. And before I forget, I should also add that this stream is in cooperations with Mortons, who are the publisher of Calum's epic tome. And if you want to get any sort of book, and especially this book, and it is really essential reading, you can do so at 10% off using the exclusive discount code MA10. The links are also in the description below, so make sure you use those. Okay, everybody can hear us. This is fantastic. I think we'll jump right into it then. And Calum, I'm going to be asking you the first question here from Nick Bayer, and he's coming at this with a very broad question, but specifically on World War II engines. How much room for engine improvement really was there? Now over to you, Calum.
So are we showing the slides, Chris?
Yes, we are showing the slides. I'm setting that up just now. 1 second. There we go. We've got it on the screen now.
Okay, so this is a gigantic question because that covers everything. So let's just make this really short and sweet. So at the bottom there, that is a current Formula One V6 turbo compound engine, which is probably the most advanced engine in the world. So it's 50% thermal efficiency, which means if you take the fuel, 50% of the energy in the fuel comes out of the engine. So that's how efficient it is. So if we look at the graph on the right, so that's a German one. So there's a lot of stuff on there. What I'd like you to concentrate on is the vertical axis. That is the energy flow from the fuel. And if you go right to the top, the very top one, the dashed line, that's the total energy in the fuel that's going into the engine. And across the bottom is altitude. That's not really that important to answer the question. So you can just look at where these lines hit the y-axis on the left. So there's 2,200,000 kilocalories per hour going in to this with the fuel flow rate. So with the World War II engine, typically, what you're actually going to get out of that from the crankshaft, that's actually what I've indicated there, energy delivered to crankshaft in 1940. So it's about 400,000, a little bit over 400,000. So you can basically see you're looking at something like it's maybe 25% thermal efficiency. And I've just put a little red note there to show where we are today with this F1 engine. So I think that's excuse me, I have an absolutely terrible cold. So we didn't want to cancel though, because you have to just go for it with these things. So you can see roughly how much more of the fuel energy we're using today than we did then. And that's kind of 3/4 of a century of progress for you. So could you have got there in World War II? No. but we certainly improved on where we were at the bottom there during the war. But it's very, very difficult to get much beyond 50% where we are now. Mind you, everyone has always said that of where they are. So, roughly speaking, we probably can use about twice as much of the fuel energy today as we could in the best World War II engine. So, that's a fairly short answer to your question.
Fantastic. Now, Scarecrow Repair has asked, what if Rolls-Royce had given a higher priority to fuel injection? What other aspects would have had lower priority, and how would engine's history have changed? And I'm going to change the slide here as well for you.
So, I'm not seeing the slides here, Chris. So at the moment, I'm just looking at my own PowerPoint. I don't know if we can get them on screen.
Yep, the new one should be on screen.
So I'm just seeing you in my background at the moment. So I can't. I've got
Oh yeah,
the
it's
slides,
showing on
but
the screen. It's showing on the screen for the stream, but not on.
okay, got it. Okay, that's how tech savvy I am. So, this is an interesting one. So Rolls-Royce didn't really need to develop fuel injection themselves because the British actually did their first tests with direct fuel injection in 1920, if you can believe it. Everyone thinks it's a German thing. It's not. It's just that they used it in the war and we didn't, not to the same extent. So we were developing it since 1920 in our research laboratories. And essentially, when the negative G problem came along, which is really the main thing which we could have solved in the Battle of Britain with fuel injection or a pressure carburetor, all the work had already been done to fix it at the Royal Aircraft Establishment. So they had already made a pressure carburetor, it's called a carburetor, but it really isn't, because the fuel comes in at a high pressure. So the air going through a pressure carburetor isn't sucking the fuel out. So it's not really a carburetor at all. It's actually what is called a single point fuel injection, which is because the fuel is going in at a single point. So there's nothing complicated about it. So it's a very primitive fuel injection system. So Rolls-Royce didn't really have to refocus their development efforts because all the work had been done for them. What they really needed to do was just accept from the RAE, which is the Royal Aircraft Establishment, their own carburetor in the late 30s, and then they wouldn't really have to have done anything. And in fact, they probably would have had more development time to use their own efforts to develop other aspects of the engine if they had used this particular fuel injection, because when the negative G issue came around, it's assumed that Beatrice Schilling's restrictor actually solved it all. It actually didn't. It just made it a bit less worse. It was still a really serious problem even after the restrictor was put in. And so Rolls-Royce actually developed their own carburetor with the SU company to try to solve this. So you can imagine how much work that was. And that was done. Cyril Lovesey was doing that. And Cyril Lovesey was in charge of Merlin development. So Rolls-Royce had their top guy developing their own carburetor. And they tested it with 2 squadrons of Spitfires and it didn't work. So it's months of work, completely wasted. But they couldn't just put the RAE carburetor on when they found this problem because it wasn't adapted to fit the Merlin they had. You know, the pattern of the bolts connecting it to the engine wasn't the same and all this kind of thing. So you couldn't just bolt it on. So by that point, it was too late to use the work the RAE had done. So I think if Rolls-Royce had taken our basic fuel injection stuff, it would have saved them a lot of time and effort. Is my rough conclusion.
Okay, thank you for that. Then Timothy Mulligan asks, I have slightly adapted this question, Timothy, I hope you don't mind. Considering the planes that we saw at the start of the war, in how far did the new German engine and aviation industry manage to catch up to their peer counterparts in other countries? And I'm switching over to your slide as well here.
Okay. So if you graph the power that the Germans got from the engines through time, they pretty much kept up with the Merlin throughout the war. But to do that, they were using different engines. So UMO went from the 210 to the 211 to the 213, and Daimler-Benz went from the 601 to the 605 to the 603. So those were all fitted to different aircraft, and in terms of power, they did keep up with everything the Merlin was putting out. So they did a pretty good job. The main problem is that this is the power at sea level. It's not the power at high altitude, which is what became really critical very quickly in the Second World War. So I haven't put the graphs on there because it gets really complicated if you start looking at the engine power at sea level and high altitude. It's quite a long essay to talk about that. But the real problem was they didn't develop two-stage supercharging in time. But that's a very similar story to Rolls-Royce and the fuel injection, because Daimler-Benz in 1936 had a DB600 engine with a two-stage supercharger on their test stand. So it's not true to say the Germans couldn't do it, although they hadn't done it. They had just had a lot of misdirection from the sort of higher planning levels, so they didn't get it into production. And when they realised there was a problem, it was too late. I think the aircraft situation, excuse me, is probably a bit more serious. I think the BF-109 is really, by the time the G model came along, I think that was the end of the road for it. I think the F model was very, very good. I think that's actually the best BF-109 in relation to the entry point in the war, to its capabilities. When the 109F came in, it was actually really good. It's probably better than the best Spitfire when it came in, whereas the G model really was maybe just about as good as a Spitfire 9 at certain altitudes, but it certainly wasn't better, and it didn't really get a lot better. It just got heavier. And by the time the K came along, because the 109's even smaller than a Spitfire, by the time they put all the extra weapons in it, if you look at a 109G, even the K, which has some improvements, the aerodynamics of the original 109, if you go and look at Willie Messerschmitt's, like, 109C or D, it's very, it looks very sleek. The later models, they're just covered in bulges and bits sticking out and, everything. It's just, so the aerodynamics are very bad. So really the Focke-Wulf 190 is much better than a Spitfire. I mean, it's an outstanding aircraft, but again, only maybe below 20,000 feet, because the engine doesn't have a two-stage supercharger. And even the D9, although it's a lot better, with the UMO 213, that's still only got a single-stage supercharger. So the high-altitude performance, even in D9, is actually not particularly outstanding. And really, they only rectified that with the D13 and the TA, excuse me, 152, with the UMO 213E, because that's got a two-stage supercharger. But if you are to ask me how many of those planes actually fought in World War II, I think it's a tiny number. I mean, it can't be more than, I can't imagine it's more than 50 planes of both of those combined ever saw combat. So it's immaterial militarily.
Okay, and then the next question comes from Jim Smithy. Why did the British not want to make that switch over to fuel injection? And I'll update the slide here as well for you.
So I already kind of hinted to a little bit of that in one of the previous answers, but I've put in here for you. I know everyone hates text on PowerPoint, right? But this is history, okay? It's not Biggles or something, or the Discovery Channel where we can just get away with saying anything we want. History is about documents, so I like to put documents on my slides because I like you to be able to see it. I'm not just making this stuff up. So I've highlighted some text for you, okay? So if we just start on the right-hand page, so this is a historical review document from the Royal Aircraft Establishment. So written after the war, they went and interviewed all the top people at the RAE, and it's hundreds of pages. So the idea of this was to try and find out what happened So they interviewed all sorts of different engineers, and they got different opinions. And if you read the whole lot, you can get quite a good balanced view of what happened. So Farron was in charge of the RAE. So he's the chief scientist, and he's a very, very clever man. By the end of the war, he's probably one of the most respected aeronautical scientists in the world. He's an extremely capable scientist. So I've just highlighted some text that he wrote through the interview that he did. So RAE made their own carburetor, and basically the firms making carburetors, as is so often the case, they're going to just start it off with, let's get a hole and we'll put some fuel in it. And they did it all by trial and error, really. So they didn't really understand the science, because carburetors are a bit counterintuitive because they're actually unbelievably complicated. The physics that goes into a carburetor, if you actually want to understand it, is absolutely horrendous. I certainly don't understand all of it, and not in real detail. So basically, the RAE came up with this carburetor and said to the firms, look, we've done this amazing thing. These companies have been doing this for 20 or 30 years. And they had all their little tricks and tweaks, and they just sort of, they just didn't want to believe that these bunch of scientists had just in a few years just solved the whole thing, and they didn't want anything to do with it. So, but it wasn't all the firm's fault. So the RAE didn't know really what the biggest benefit was going to be, which is immunity from negative G cutout in the dive. So they're going to Rolls-Royce and said, look, come and get our injection carburetor. And as I've said before, I keep saying carburetor, but the injection carburetor is primitive fuel injection. That's what it is, because the fuel's coming in under pressure. And Rolls-Royce said, well, why should we have this one? And, they just said, oh, well, it doesn't ice up. And then Rolls-Royce sort of said, well, yes, but we've realised that if you put 2 or 3% alcohol in the fuel, it stops it freezing up anyway. So the RAE couldn't actually sell their own product effectively because they didn't even know what some of the benefits were. So I think it's a combination of different errors, and it's hard to blame any one person. But I think that they didn't really realise what the benefits could be, the true benefits. And I think it all comes down to the testing. If the testing had been done properly, they would have realised the negative G problem in the mid-30s, and then they could have maybe sold this to Rolls-Royce. They could have said, hey, we can solve this problem, but they didn't know it was going to solve that problem, so their sales pitch wasn't good enough, basically.
Okay, next question then here from Frank C. The obvious is more horsepower equals a better aircraft. That's then there must have been the environmental constant, which is a barrier to performance. At some point, a spinning propeller must, of course, reach an RPM at a blade angle where any faster makes no performance improvement.
Yeah, so you do really need to speak to an aerodynamicist to get a proper answer on this, but I've spoken to aerodynamicists, so I'm basically just going to repeat what they've told me, because it's not my profession, but I dabble. So essentially, I don't have a graph. I didn't have time to go and get a graph, but there are some. If you graph different propulsion methods, like a propeller, a turboprop, and a turbojet, across the speed range of efficiency, the propeller is very efficient at low to medium speeds. That's why it's still used today for low, medium speed aircraft. It's the most efficient way of doing it. And propellers are coming back for some low to medium speed stuff. In the middle speed range, you want a turboprop because you get a degree of jet thrust. But if you want to go supersonic, you need to have a turbojet. So the propeller, the efficiency goes down as the speed goes beyond a certain point. So it's almost impossible to go supersonic with a propeller. I believe it is theoretically, it's not outside of the laws of physics, but no one has actually managed to do it. And even the Thunder Screech, which is an unbelievable plane, didn't manage to do it. So that had a specially designed propeller that spun supersonic, which you're not supposed to be able to do with propellers, right? The tips are not supposed to go supersonic. This one was designed to go supersonic, and even it, which is a turboprop with nearly 6,000 horsepower, didn't go supersonic. So I think probably about the best you're going to get is with a Reno Racer. So that's a P51 Mustang, or what's left of one. There's probably not very much Mustang left in that, actually. It's an unlimited racer. So that's been flying with about 4,000 horsepower. So that's over double World War II power. And you can do about Mach 0.75. So 550 miles per hour. So that is probably the practical limit that you're going to get.
Okay, fantastic. Then Joe asks, why did Europe go with the V12, mostly water cooled? There were a few air ones, but mostly water cooled. When there were already some radial engines, was there simply that the belief that the radial is causing too much drag? Japan, of course, went mainly with air-cooled radials. The same reason the US Navy went air-cooled radials, simply because they were easier to maintain.
So I don't have enough data to answer the question for you on Japan or the US Navy. I don't like guessing. I don't have the data, so I'm going to answer the bit I can answer. So I've put another bit of history there for you. This is a really funny memo, so I really encourage you to read this. It's really funny. So this is in the Air Ministry Focke-Wulf 190 file, and it's just after they've started encountering it. And you can see this, this guy's just, it's a really stupid letter, isn't it? He's just getting annoyed. What is this about the Focke-Wulf 190? And I've highlighted the bit at the bottom. And just read it, please. You know, I don't want to read all the text, but he's basically saying, you know, this can't really be a serious aircraft because it's air-cooled, and everyone knows that to have a good fighter, you've got to have a water-cooled engine. So I think in Britain, all of our policy was really around the success in the Schneider Trophy. So that's all liquid-cooled V12s. So I think that impacted our thinking. So really the Americans, I think roughly in parallel with the Germans, but I think the Americans might have got there slightly earlier, started doing really serious aerodynamic studies on how you would streamline a radial engine. And so I think the Germans took this research and did their own stuff on it, roughly, fraction later than Americans did. So there's just a little wind tunnel model that's done in Germany I've put in there, just to show you some very early experiments they did with saying, well, okay, how do you shape a duct around a radial engine in a way that's going to be aerodynamic? So the Focke-Wulf 190 really existed because this scientific work had been done in Germany in the late 30s, and it had also been done in America. And in Britain, that work hadn't really been concentrated on. So we didn't think you could have this sort of aerodynamically streamlined engine cowling around a radial engine, which the Focke-Wulf 190 definitely does. And you had all these stick in the muds writing these pretty stupid letters like this. So I think in Britain it was a pretty late realization. Chris, could we have the next slide, please?
Of course. There we go. By the way, I think I also saw this letter in the National Archives once. It's a good one. It's a good one, yeah. Yeah, the next slide
So
is up.
cool. So, but we did realize. So you can see about 1941, they started proposing putting the Bristol Centaurus into the Hawker Tornado. So I think it didn't take us a long time to realize that you can make a very fast fighter with a radial engine. So I think once the Focke-Wulf 190 came along, that completely changed the British thinking on it. But as I say, the Schneider Trophy and the fact that the scientific research on streamlined cowlings was done in Germany and America is what drove the sort of British reluctance to believe that you could have a streamlined radial.
Fantastic. Now, transitioning to the next question there. Thank you, Joe, for submitting the previous one there. We have Nicholas. Why was the German aero engine development and other related areas so fractious and mismanaged as it was? I think this is going to be a fun one to reply to.
Yeah, so it's all down to politics. So there's absolutely no question that Germany at the time, actually probably still now, really has a very unusually high number of very, very highly qualified scientists and engineers. Germans are very rigorous with their work, and I know a German guy. This is a joke, but I think there's a lot of truth behind it. I once asked a German guy. I said, "What's your worst nightmare in a work situation?" And he said, "Oh, that's easy. It's just to be asked to do something that I haven't been trained for."
Yes.
Whereas if you ask someone in Britain to do that, they would probably say, have a think for a minute and think, I think it's 50-50. I could pretty much figure it out in time to do the job, you know? But Germans don't like that. So when we're talking about what went wrong in Germany, it is not that the German engineers are stupid. This is not the problem. So it's a management problem. So we can talk for hours about that, but there's just one example I'd like to make here. So on the right, we've got a page from Bullman's memoirs. The unpublished ones are better. They were published by Rolls-Royce Heritage Trust, but they've trimmed out some of the more fractious remarks. So the unpublished one is best. You can go and look at it at the RAF Hendon Archives in London. So Bullman was in charge of British aero engine development at the Air Ministry and later Ministry of Aircraft Production. So that's Bullman in the middle, sitting at the desk. And to his left, that's Helmut Saxer, and he was his opposite number at the German Air Ministry. And the two of them were very good friends. So they used to meet all the time in the 30s, go out drinking, all this kind of thing, meeting at conferences. They knew each other very, very well. So Bullman went to meet Saxer in Germany, and in 1937, and other dates as well. And Saxer was basically saying to him, you know, I've been talking too much. I just don't get on with these military people who are running things now. But he means the Nazis, obviously. And he basically said to Bullman, I'm going to be sacked any day. He knew it. At that point, he was in charge of engines at the German Air Ministry. So that's exactly what happened. So he was too good an engineer to just get rid of. So the Nazis sent him to BMW. So he was so good that even getting sacked, he was sent off to BMW to basically be the chief engineer. So that's how good he was. And so Saxer should have been managing German engines through the whole of the war in the late 30s, but he was sacked. So the quote underneath the photographs is from Bullman's unpublished memoirs. So he's relating here to his last conversation with Saxer, which he had in a Brauhaus in Munich. So that's what he says is his last conversation with Saxer. And Bullman said Germany had lost a great leader. So that's the opinion of the British head of aero engine development. So without spending hours on it, that's basically what, if you want me to name one thing, that's what went wrong with German aero engine development management.
That's a very interesting story how individuals can have a very profound impact on the future of the industry, especially in a situation like this. Moving over to the next question here, once again by Nicholas. Was there any merit in developing the BMW 801? Were the Germans better off focusing on V12s? Now that's an interesting question.
Yeah, it's a very good engine. They should have kept developing it, but there were two big problems. One is that because Germany had run out of a lot of key precious metals or strategically significant metals like nickel, not run out, but had such a low level they couldn't really use them in the right amounts. This made the engines very thermally sensitive. So there were parts of it which basically would start corroding at high temperatures when they shouldn't. And this is a real problem for air-cooled engines because they run hotter than liquid-cooled engines, right? So when the German valves in the engine started going wrong, BMW were the first firm to encounter the problem. That's because the 801's an air-cooled engine. So the exhaust valves had the amount of nickel reduced, they corroded, induced detonation, and the pistons start melting. All kinds of problems. Not very good problems, and so that's a problem which is exaggerated if you have an air-cooled engine. So they expended huge effort just trying to keep the thing running properly. So that was a big problem. So there's a bit of alternative history going on here. It was difficult because they'd run out of the metals, but I think what you're probably asking me is, was it fundamentally a good engine? I think that's really what you're asking me, and yes, it is a good engine. There's a bit of a weakness in the supercharger, but BMW had done a great job. So the BMW turbocharger here, it's a really fantastic piece of kit. So if you go to it's very advanced. You've got hollow turbine blades. It's a very, very nice piece of engineering there. If we go to the next slide, please, Chris.
Yes. There we go. We see the whole engine now set up.
Yeah, so that's the BMW 801 TJ. So that pretty much flew right at the end of the war. I think only in the Junkers 388. There might have been a couple of different models of that, but it only flew right at the end of the war. But it's a really, really good engine. If they hadn't had some of the problems, maybe they could have got this flying a couple of years before, and then it could have been a really very militarily useful piece of kit. So yeah, I hope that answers the question.
Fantastic. Then the next question is here on also from Nicholas. Assuming the Germans managed to implement proper timely workarounds to material shortages and avoided the developmental policies they committed, how much more potent would a Luftwaffe fighter force have been?
This is a bit multifaceted because you've got to solve several different things. It's not just the materials. To try to answer it, it would have made a huge difference had certain other things also been fixed. So to give you some idea, so this is Edgar Peterson. He's in charge. He's the chief. He's basically in charge of Rechlin. So that's the Luftwaffe testing establishment. So that's like Wright Field in America or Farnborough in the UK, or the RAE at Farnborough. And so this is his report, 16th December 1941, on the Focke-Wulf 190. So he says Luftflotte 3 have no confidence in the safety of the BMW 801, having to run it under 50% full power. That's because of the valve problem that I was talking about with the low nickel valves that were corroding and destroying the engine. So you can see what he said. So if that hadn't happened, we all know what the RAF thought of the Focke-Wulf 190, and I don't mean the stupid letter that Chris and I just showed you. The pilots did not enjoy fighting the 190. But most of the 190s they fought early in the war were all running derated engines, so they were not allowed to run full boost because it was they couldn't. They blew up. So the Focke-Wulf 190 was really dangerous, and it could have been even more dangerous without these problems. So can we have the next slide, please, Chris?
Yes, it is up.
So there's a few other things you need to solve too on the water-cooled side. So this is a stenographic meeting record, 27th November 1942. So this is recorded by like a court stenographer on a shorthand typewriter at the RLM conference. This is spoken word record. This is not a summary or what someone thought they said years later. It's word for word what was said. Well, that's my translation, so you'll have to trust me. But unfortunately, you can't get to these records at the moment because IWM have not reopened their archive, so you can't get to the microfilm.
IWM being the IWM again. Yeah.
Anyway, so Messerschmitt is getting really fed up at this meeting, being criticised, and so he basically says, well, yeah, okay, the 109 needs to be faster, but I'm having to put radiators on my planes that are twice the size of the English. And Erhard Milch, who's not an engineer, he's a pretty sharp guy, but he's not an engineer. He just says, how have we not noticed this? Eisenlohr. Now, do you remember where we were a couple of slides ago when I was talking about Saxa? So guess who took over from Saxe? Eisenlohr. So Eisenlohr says we can't use small radiators because you need to use very high water pressure and we get leaks. So the reason the British had very small radiators compared to Germany is because they use very high water pressure. So you can use very high coolant temperature. If the temperature of the coolant is much higher, you've got a bigger temperature difference between the coolant and the outside air. You get much better heat transfer, so you can have a much smaller radiator. So that's what we were doing, but it requires years of work. You can't just put a big pressure cap on the release valve and say it's high pressure, because everything, you have to develop high pressure fittings, all kinds of things, and they hadn't. Even though it had been written in the specification document in 1928 that the Germans needed to develop high pressure cooling, and they didn't do it. So at this point, Milch gets pretty annoyed, and this is seriously what he says. He threatens to dissolve the Daimler-Benz design office and send them to Junkers. That's how annoyed he is. So that's seriously what he said. So can we have the next slide, please, Chris?
Yes, it is up.
So that's what happens to a German radiator of the type that's in a 109 if you put high pressure through the cooling system. So the radiator on the right, it's the same design method. I think it's actually, the one on the right is actually from an annular radiator around the nose. So I think it's probably from something like it could be TA. It could be a TA 152 radiator actually, or a D9. Anyway, on the left, that's the radiator tube from a Messerschmitt 109 at the Royal Aircraft Establishment in 1940, and they've cut it down the middle. And how they made that is, it's a round tube which they squashed flat, and there's a little pip in the middle so that when you squash it flat, it doesn't close up and you can get water through it. So what do you imagine happens if you pressurize that? It blows up like a bicycle tire, because it was a tube and you've squashed it and now you pressurize it. So when the Germans tried to run high pressure cooling, the radiators did what you see on the right hand photo. So the tubes all blow up. And of course, Messerschmitt didn't make the radiators. These were all made by companies like SKF or Bayer. And it's years of work. You can't just pressurize this stuff and start doing this at the drop of a hat. It takes years of development work, and people like Eisenlohr hadn't put the time in. They waited till they were getting shouted at in a conference to do it, and then you've got no chance. That's it. So there's a lot of different factors to address. They would have needed to sort the material shortages out and solve a couple of key technical difficulties like this with the radiator. They knew what to do. They knew they needed to do it in the 30s, but they just didn't get around to it. So there's a few things to solve there. But I think it would have made the Luftwaffe, I'm not going to say it would have changed the course of the Battle of Britain, but I think at the very least it would have made the RAF missions over France in 1941 basically impossible. They already became impossible when the Focke-Wulf 190 came in, but I think it would have been far worse. And I think the 109F would have been rendered much more lethal.
Can I just add a question to that? Since we know that Eisenlohr replaced Strache, what was Eisenlohr's credentials in this fact? I mean, this is not a random guy that was put into position, or is that in fact what happened?
Eisenlohr's got a similar history to most of these people. So he's a pilot from World War One.
Okay.
He's not a stupid guy. He's reasonably technically trained. So after the war, Eisenlohr was quite a respected person in German aviation. He was involved in German aerospace, into the 50s and 60s. So I'm guessing a bit here. My best guess is that Eisenlohr was a bit of a boffin type. I think he probably just wasn't cut out for sort of high technology management, which is, you've got to have it's no good just being clever. You've got to have you've got to be taking information from numerous sources, dealing with very complex, constantly developing situations. You've got to be able to deal with pressure and stress. if you can't do all of those things, you can't do that job. I think he wasn't stupid, but I don't think he was cut out to be a sort of top level scientific administrator.
Okay, then moving on to the next question. This is a fun one. What unexpected fact or opinion did you take away from researching and learning about the development of these engines and those who actually made them? I'll update the slide here as well.
Okay, so there's a few fun things. One of them was so the first presentation I ever gave is when I was working at the F1 engine factory at Brixworth, which is the Mercedes engine factory. And a few guys were bored at lunchtime, and they knew I was researching for this book. And they said, let's not walk to the sandwich shop at lunchtime. Let's go through to one of the lecture theatres. And hey, why don't you go and do a PowerPoint? So I put this PowerPoint up, and so this is the little piece of the UMO 213. So this goes in the end of the crankshaft. So the oil comes in here, and you get better bearing lubrication because the oil's going through the middle of the crank instead of fighting to put it in through journals drilled in the sides, because you've got the centrifugal action of the crank spinning tries to chuck the oil out, right? So if you try and put the oil in, it doesn't work as well. So I put this up on the screen, and one of the Mercedes engineers just he did that. It's I think it's a meme that's going around Twitter at the moment. But there's Leonardo DiCaprio just sort of sitting on his couch, and he points at the TV.
Yes, yeah.
So he literally did that, and he's like, "That's exactly what we've got in the F1 engine. It's identical. It's I mean, even the size of the drillings is the same. It's indistinguishable." So that was really stunning. That there were several things that were, not just conceptually the same, but like basically identical. So that was pretty stunning. So could we have the next slide, Chris?
Yes. There we go.
This was amazing as well, and it just goes to show you that you've got to go and read archive stuff, because so often it just has no bearing on what you think you know about the subject. So open up this file. British tests of direct fuel injection, date June 1920.
Yeah,
so,
top right there. Yeah, I see the date.
So, that was unbelievable. So that was just, I really just knew right there and then, okay, I'm going to forget everything I thought I knew about this subject. I don't, forget about it. So there's loads of things, but I think that's two little examples of things that really shocked me.
Fantastic. Now for the next question, what was the octane values the Germans produced during the war? That was from Joe. And the slide is up.
Thanks. So this is so hard to answer. My recommendation is you completely forget about octane numbers. They're almost worthless, and I wish everyone would stop talking about them. So they don't mean very much. So we don't have time to go into all that there right now. But just to show you here, so this is a test at the Shell Thornton Aero Engine Laboratory of BMW 801D. And so the y-axis there on this graph, you basically just consider that to be the power output of the engine, okay? So blue fuel, that's the German service fuel, B4. So that's about 88 octane according to the tests that we would have done. BAM 100, that's British Air Ministry 100 grade. So, and the top green fuel, that's German C3, that's their sort of high power stuff. So on the BMW engine, Allied 100 octane makes less power than the German high octane fuel. But depending on how you test them, see, our fuel ended up being called 100 130, and there are some tests of the German fuel where it's rated at about 98. So it just forget about octane. It's a really stupid rating. So if we could please go to the next slide, Chris.
Yeah, that's up.
So this just starts to show you that the horrible rabbit hole of fuels that you've just gotten yourself into. So what the Germans realised way before anyone else realised is that the octane value of the fuel changes completely depending on how rich or lean the air fuel mixture is. So it's a complete waste of time testing a fuel at one point and saying that's the octane number. Because, for example, if you look at the line, the solid line, that is Allied 150 octane fuel. And according to the German method, there, one of them, it's 107 at rich mixture, and it's about 102 at lean. And the patterns change. So if you, some of them are very flat, and some of them are very sweeping and curving. So what this basically means is, under this particular test rating, so the allied fuel would get very high power at rich mixture, and then at lean, the power drops right off. Then there's a different test method. I've said DVL test method there, and they rated the 150 octane about the same as the German C3 at rich mixture. So that's the kind of dashed pencil line. That's using a different test method. So honestly, it's a complete waste of time thinking about octane number, because it's completely dependent on the engine. The octane numbers are all derived from standard test engines, which are like these great big static cast iron things, which are from about 1910. You know, they run at about 1,000 RPM and they churn out these numbers. They're okay to compare fuels, but it doesn't really have any meaning compared to how it's going to behave in the aircraft. So to answer your question very badly, so the German fuels, the octane, according to their rating, would be about 100 was the best they produced. That's actually about the same as we did, because 100, 150, the two numbers, 100 is the octane at lean, 150 is the octane at rich. So that number is at two different air fuel mixtures, and it's not dissimilar from the German one, which on the MON octane scale is 98. So yeah, it's all a bit difficult. So if you can go to the next slide, please, Chris.
That's up, yes.
So what you end up with here is that to understand what fuel's going to do, you end up with a 3D map. So the y-axis is the maximum boost you can put through the engine without getting knock. The axis coming in and out of the page is the temperature after the supercharger. And the axis going left to right is the air-fuel ratio. So how much boost you can put on the engine is a function of all these different things. You can't just say, I've got fuel of 100 octane, I'm going to put this how much boost on, because it depends on all the things that are going on. So I'm sorry, that's not a very nice answer, but it's really complicated. So I hope you've at least learned a little bit there.
Okay.
So the next slide, please, Chris.
Yes, there we go. Is that the next question then? For French engine development?
Yes.
Okay. In that case, we'll just have a very quick reminder to everyone in the chat to, of course, consider picking up the Secret Horsepower Race. Put that up on screen right now. It is a fantastic treasure trove of information, and Calum here is, of course, very graciously giving us his time to answer all these pre-submitted questions. We have a couple of pre-submitted questions still coming up from patrons and channel members, and then we're going to open them up on the floor for about 1 more hour until 7 p.m. local time here in the United Kingdom. And we're going to give priority, of course, to Superfangs, and then also Hookanaut in chat, our volunteer, is in fact collecting all your questions as well. So make sure you submit those. And just as a reminder as well, we do have this fantastic offer here by Mortons, the publisher of the book, The Secret Horsepower Race, 10% off any book you order at Mortons, if you order it directly at Mortons, with the link in the description below. So if you want to get yourself a fantastic run of books, including The Secret Horsepower Race, I highly suggest that you check that out. Now, let's go back to the questions column then. And I will be jumping into this interesting question here about the French engine development. Why was the French engine development so behind, asks Airborne Cigar. Now, there's another author who touches on the politics of it and the vagaries of the Air Ministry, the French Air Ministry. And then you have other accounts that look at the political reasons. Both Hispano-Insulza and, of course, Gnome Rone, I hope I pronounced that correctly, had the potential to produce much more powerful engines, but that didn't happen. And this is also similar to questions submitted by Miss K and Fouquet Egon. And I will be changing to the next slide. There we go.
So are we looking at the SE5A now?
Yes, we are.
Good. So I only have quite a limited number of archive files on this, but I'll tell you what I've got. It's not a full answer, but it's a partial answer. So basically the history is roughly in World War One, French aero engines were really world leading. They're pretty much the best for most of World War One. So Britain was using French aero engines in many of their fighters. So the SE5, which many people will tell you is the best fighter that we fielded, used a French engine. Roughly speaking, France kind of dropped the ball at the end of the war because it was the end, and Britain sort of caught up by maybe 1922. Many of you will know the Napier Lion, so Hispano, Farman and Renault basically all made copies to some degree of the Napier Lion layout. And essentially in the mid-20s, the French had a lot of very lucrative contracts to supply engines, and basically it was just a complete cash cow. And they were just happy and said, look, we're making so much money, we're just going to keep making the same engines for years and years and years. And they made loads of money. And then the Schneider Trophy started progressing a bit, and it got to about 1929, and the French realised, oh God, we're light years behind. This is actually a really big problem, and we can't just keep all our lucrative contracts are coming to an end, and we're really behind. So roughly speaking, as far as I can tell, they basically just stagnated for too long in the 20s because they had all these contracts to just keep making the same engines for a while, and they just fell really far behind. So can we have the next slide, please, Chris?
Yes, that is up.
So this is another, this is some from Bullman's papers. So this is the guy running aero engine development at the Air Ministry in Britain. So these are from his papers. So this is also at RAF Hendon, not from his diary. So these are from papers he wrote just prior to the war. So I think he'd been on a visit to France. So this is just what he's written. So he wrote an essay on what had gone wrong with the French aero engine industry, because he was aware they used to be very good. So he was trying to work out in this essay what they had done wrong. So he's basically saying, I don't have more information on this. There seems to be a divided technical control between the French War Office and the Ministry of Marine. So that seems to be something that was taken advantage of by some of the firms to sort of probably pull the wool over the eyes of some of the administrators. So it's about an 8-page essay, but that's kind of a pertinent bit with regards to the politics of it. So can we have the next slide, please, Chris?
Yep, that's the Farman engine up.
So so the Farman engines, they're quite interesting. So a lot of this French stuff, it's all inverted. So that's very, very interesting. So we can see again that having upside down engines is nothing unique to Germany at all. De Havilland also. So that's quite an interesting one. Can we have the next slide, please, Chris?
Yep. Yep, that's up.
This is probably my favourite French aero engine from the 30s. It's not perfect, but this is a Delage. It's very small, 8 litres, but 440 PS. It's really powerful, and I think it's a really nice engine. So basically, the French Air Ministry, I don't know if that's the proper name for it, didn't give Delage a contract to develop this, and they went bust. Not all that long afterwards. But if we can have the next slide, please, Chris.
Yep. That's up.
This little engine was used in the, I'm not going to pronounce this correctly. Kellner Becquerel
Yeah, very good.
um,
Yeah.
um, aircraft. So that's 1933 air race. So it was used. There was a crash involved, but I think that's the point. Is I think it's a really nice engine, and so I think if the French Air Ministry had really just, I think what they really should have done is invested in Delage, because they looked like they had some really really good designers, and they probably just needed some more resources and some money, and that wasn't forthcoming. So I think that was a problem. Could we have the next slide?
Yeah. Can I just ask, do you know if Delage was a private company or if it was already nationalized at this time?
I don't know the answer to that. I'm
Because,
sorry.
yeah, next slide is up.
I could have just Googled it and lied and pretended that I knew, but I'm afraid I don't. Google will know probably, but
Yes.
I don't. So the Hispano Suiza 12Y. So it's a Spanish company, but the main manufacturing place for these engines is in France. So that's the French connection. So this engine, they did a lot of work putting some nice widgets on it. So there were versions done with some really nice things like the Sidlowski Planiel supercharger and stuff. But the problem is the base engine is just about, by World War II, this is 10 years out of date. So we've got 2 valves per cylinder. It's just not going to cut it. And if we could have the next slide, please, Chris.
Yes, it is up.
So the exhaust pipes and the inlet system are on the same side, and this is typical of really old car engines. This is really bad. The reason that's bad is that the exhausts are really hot, and you're putting the fuel in where it's really hot. The fuel and all the inlet air is getting really hot, which is the worst thing for efficiency you can possibly have. So I think the engine is just 10 years out of date, which is not to say it couldn't have been updated, because, when the Merlin came in, the Mark 1 Merlin is a disaster. It doesn't work at all. So it's not to say that, you need to have something which is perfect and you never develop it. But I think that this engine needed to have, at least half a decade of development put into it, which, and the basic architecture, which wasn't done. So that meant that despite some clever things that were tried on the 12Y, the fundamental architecture is too outdated.
Okay. Moving on then to the next question by Miss K. What sort of problems were faced with the Merlin and Packard engines early on, and how did they compare to each other in terms of reliability and maintenance? Oh, sorry, I was reading the wrong question here.
Yeah,
Yes.
that's
Slim Shade Millionaire is up here. After capturing some BF-109s, the Allies would have seen the variable speed supercharger installed in the Daimler-Benz engines, but never, to my knowledge, adopted the system. Why did the Allies then not utilize this variable speed supercharger, despite the benefits that seem to be there?
so they did use it, but it didn't really come out in time for combat. But just to describe it a little bit, so on the right there, that's my photograph. That's the fluid coupling. So it's basically it's not really a gearbox. It's a variable slip. So you can't speed it up, but you can remove speed from something. So by varying the amount of oil in this sort of cavity in the middle, you can slip the speed. So it's more efficient because you can slip the speed instead of using a throttle. So that's kind of what it is. So that's maybe worth 10% engine power at sea level. So if we just have a look at the next slide, Chris.
Yes, there we go. It's a graph.
So that's a graph. So that's a German graph from the papers of Dr. Coleman. So Coleman patented the fluid drive coupling. So I translated Coleman's memoirs, which are now available to purchase from the American Society of Mechanical Engineers. We've only sold about 70 books because it's an academic publisher and they are unbelievably expensive, so no one can afford to buy it. It's ridiculous. Don't buy it. It's like £100 or something. It's completely crazy. Just email me a question or something, okay? Go to the next slide.
Yes. Yeah, that's not a graph. Oh no, that's overlay
So
now.
it's an overlay. Okay, so basically, if you've got a two-speed mechanical supercharger like a Merlin XX, so this is engine power on the y-axis and altitude across the bottom. So with a Merlin XX, you'll get the engine power will be like the blue lines. So it's a sawtooth, double tooth sawtooth. So these are the gear change points basically. And you lose the power because you're having to throttle below it, so that you make a loss there. So if you've got a perfect variable speed drive, you get the red dashed line. So what you actually get from a fluid coupling is the yellow line because there's some inefficiencies there, which mean you don't get the perfect. So basically, the hatched area is a power advantage area from the fluid drive to not fluid drive. So it's worth about 10% engine power at sea level. So this is pretty important in a plane for takeoff. So it's quite a nice advantage, there's more to that advantage than just combat. So can we go to the next slide?
Yeah, that is two engines.
Yeah. So on the left, that is the Allison V1710 two-stage supercharger. So it's an auxiliary supercharger, which is it sticks like a foot out the back of the engine, and people say, why wasn't it used in stuff like the Mustang instead of Merlin? Well, you can see why it wasn't used because it's too big. It's very nice though in a lot of ways, but if you have a look just behind the supercharger impeller, so it's kind of if you look at the sectioned bit right at the back, there's a bit of yellow paint. Just above that yellow paint, that's a fluid coupling. So the Allison engine has fluid coupling, which is identical to the Daimler-Benz version. And we wanted to use it in the Merlin. So Jeffrey Wild of Rolls-Royce, he had worked with Daimler UK and knew about fluid drives. And he went to Stanley Hooker and said, we should use fluid drives. So he went to a company called Sinclair Fluid Drives in London with Hooker very soon before war broke out, and they had a scheme laid out. So this is a scheme for the Merlin to have a fluid drive coupling for the supercharger. And basically, when they were right in the middle of scheming this, the Battle of Britain happened, and it was chaos. And they just said, "I need hundreds of Merlins made now," and it got dropped. They had to can it. So it's not quite true to say we didn't use it. So can we have the next slide, please, Chris?
Yep.
So also, if you look, this is a bit of a cheat because it's not quite World War II, but it was designed in World War II. So if you look at a Boeing B-29, so the version of that, which was flown a little bit after the end of the war, has turbo compounding on the R3350 engine. And governing the speed change between the turbines and the crank are three fluid couplings. So, and they're identical to the couplings used in the Daimler-Benz engine. So I'm cheating a little bit there because they designed it in World War II, but it did not see operational combat in World War II over Japan. The plane did, but that specific engine did not. But yeah.
Okay. Then moving on to the next question here by, again, Slim Say Millionaire. Why did the British go centrifugal flow jet engines over axial flow engines? And what are the benefits and downsides of this choice?
So I would question your question. I'm going to show you why. I wouldn't say we did go for the centrifugal, certainly not exclusively. And there's a lot of, I think, slight misunderstanding about the timeline here. So Griffith on the left here gets a lot of flack because he was one of the first people who spoke with Whittle and said, I don't think your idea is going to work. And everyone says, oh, this Griffith guy must have been some sort of, real cretin because he was getting in the way of Whittle. I don't think Griffith was a bad person or he was trying to delete the idea. Griffith himself wanted to have an axial jet, But his idea was not to use the thrust of the jet specifically. His ideas were basically a turboprop, but it went axial. So that's Griffith's first little test jet in the middle there. And Griffith did that years before Whittle did. So can we have the next slide?
That is up.
So I feel a bit guilty here because it's a slight. I was not able to ask for permission to use these images, but because sadly Dr. Armstrong, who wrote this paper, died a couple of years ago. So Frank Armstrong, who wrote the paper I've taken this from, he was the director of the National Gas Turbine Establishment, and I knew him and met him. So I'm just going to say that if he was still alive, I think he would said, yes, it's okay, you can put this in your PowerPoint. So let's just have a look at the timelines here. So Griffith is really doing he's 3 years ahead of Whittle with his thinking about jets. And so if you look 1935, so this Anne compressor, that's on the top right there. And the F2 engine, so that's an axial turbojet, so that's running out of 1942. So it's a few years behind the first engine run with the Whittle jet, but Britain was running axial and centrifugal turbojets. So we went for both. It's just that the centrifugal design is a lot simpler to get right. The axial, you need a lot of extra science to get the axial design working. It's quite a tricky thing, so it takes a bit more development effort. But Griffith was right. The axial design is the winner for a military jet. Who's flying military jets now with centrifugal turbojets? You'll get them in some helicopters. So Griffith was right. So I think we should try not to be too harsh about his early opinions about that. So if we could just have the next slide.
Yep, that's up.
So Griffith also didn't make his life as easy as he might have done. So the centrifugal jet is on the right. So you've basically got a double-sided supercharger disc, which is pretty much identical in shape to what you would have on the supercharger from the Rolls-Royce R engine, which was double-sided. So you've just got a supercharger from an aero engine, a shaft, a turbine, and a combustion chamber. So it's quite simple. Griffith came up with this counter-rotating design here. I mean, you don't need to understand what's in it to see that there is a difference in complexity here. So the axial stuff took a lot longer to get going, but we did both. And so if we could have the next slide.
That is up.
So I also like to say it's not just Whittle who struggled with getting funding. So this is a report. This is what was said to Griffith in 1930 when he tried to get funding for his axial jet. The panel considered, so this is not Griffith, this is addressing Griffith. The panel considered that the present state of knowledge is superiority of the turbine over the reciprocating engine cannot be predicted, and I've got no intention of advocating large expenditure. So everyone was struggling to get this stuff through. So you can't just level this at Griffith. So get on the next slide, please, Chris.
Yep, that's up.
So again, just saying here, so RE test. So you've got the F2 axial flow gas turbine. That's 1940.
Mm-hmm.
So and then the Whittle on 1942. The Whittle one was tested first. That's just the date on the particular test of this photo. I'm just making the point that we did both. So I'm not sure it's easy to say that we concentrated on one more than the other.
And then a question here from Boomerang Pigeon. I would like to know if Calum has been able to do any research on Japanese aero engines specifically. I am curious to know how their technical solutions to shortages of alloy elements compared to the Germans.
So I've got very little stuff on Japanese stuff, partially because I can't read Japanese, also because Japanese are not a terribly open society, and my approaches to Mitsubishi Heavy Industries to be allowed into their archive in Japan have not proved successful so far. I'm gonna keep trying. I'm gonna keep trying. I'll get there one day. Well, I do have a few things from our intelligence reports, so sort of U.S. naval mission reports and some British stuff. So a few interesting things is the Americans are here really saying that. Well, you can see what they're saying there. Japanese propeller design is 5 years behind the USA, so that's a really really serious problem. Um, so they basically said um, that the we've got some background noise going on, Chris. Can you hear that, or is that just me?
I don't hear any background noise at the moment.
Okay, okay, it's gone.
Okay.
I don't know what's going on there. So yep. So they basically said that the poor propeller design was really hampering Japanese efforts to make high altitudes, high performance fighters. I would say aviation fuel supply was probably also a really, really, really serious problem. So it says here the fuel was basically all 92 octane or less. Going back to what I was saying before, you have to treat these figures with a degree of suspicion, but I think you can basically say that's a big enough difference that the fuels are probably pretty primitive. So if we can have the next slide.
Yeah, that's up.
So this is a pretty good one. So this is an evaluation of Japanese Sake 12 radial engine captured in Saipan. This is quite interesting. So it says basically saying that from the inspection of earlier engines that alloying elements were used lavishly and wastefully. So obviously in Japan near the start of the war, they were probably in pretty good position. But you can see here they've written that these changes started to be made in a bit later on, started to make the same changes that the Germans made in 1940 and 41. So that's reducing the amount of chromium and nickel in their steels. They've said they didn't go as far as the Germans did as of December 1943. And they've said that even the Japanese economy steels still leave a considerable room for further savings. So I would say that probably the Japanese, with respect to shortage of materials, were not in quite as bad a position as the Germans were. If we could have the next slide, please, Chris.
Yep.
So there's some pretty good evidence that they are behind in some areas. So this is spark plugs. No one's interested in spark plugs, so no one ever writes about spark plugs. But the engine doesn't work if you don't have spark plugs. So they're important. Just because they're small doesn't mean they're not interesting. So this is a comparison, a British comparison of German and Japanese spark plugs. So what's interesting is, look at the electrodes. So the Siemens plugs are all pure tungsten. So tungsten is very well known for having an incredibly high melting temperature. So you need to, it's about 4,000 degrees melting temperature for tungsten. That's why you have it used as elements in light bulbs, because expensive light bulb. And the Japanese ones were just made of heat-resisting steel. Interestingly, the Bosch spark plugs, they look pretty crappy, to be honest. So I don't know what the reason is for that. But I know Bosch German spark plugs in the war were pretty ropey, actually. So the insulators, the German ones are all they're sintered ceramic insulators, and the Japanese ones are all mica. The reason that's really important is what everyone discovered, including the Americans who loved to use mica, or even up to about 1942. So the tetraethyl lead in the fuel eats mica. So they started putting more and more lead in the fuels from sort of 1930 onwards to get the power up. But it destroys the mica. It literally eats it away very, very quickly. So the ceramic insulators are not affected by tetraethyl lead. So the Japanese plugs are pretty bad. So they obviously did have some problems. It's interesting they haven't used tungsten for the electrodes, because I have seen German documents saying that they were hoping for supplies of tungsten from Japan by U-boat. So that's interesting. So can we have the next slide, please, Chris?
Yep.
So there's a really good series of reports which you can find. Some of these are online. So I think if you go to the Fischer-Tropsch archive online, if you Google that, you can find PDFs of some of these they're just in black and white. So I've got some of the ones which are colour, which just gives me bragging rights that I photographed the originals. It's not more useful. So I just want to say that I think fuels is maybe a very important thing. So can we have the next slide, please, Chris?
Yep, that's up.
So basically, when the US Navy went into Japan to look at fuels, they discovered that actually Japanese people, they're pretty clever. And this Japanese stuff wasn't all backwards. And even when they were really struggling, they were still doing very, very clever stuff. So Japan also made synthetic oil facilities because they needed to convert coal into oil, paralleling the work in Germany. So that's very, very interesting. So that was all driven by shortages. And the Japanese started heavily investing in this from 1921. So really ahead of schedule, if you like. So can we have the next slide, please, Chris?
Yeah, that's not a table.
Yeah, so that's just, again, you don't need to memorize that. That's just the location of the Japanese synthetic oil and fuel plants. So just to give you an indication, you can see that the fuel output. So this is quite a big program. And again, everyone talks about German synthetic fuel, but actually the Japanese were doing a lot of it too. So that's, I think, something we should know more about. So the next slide, please, Chris.
Yep.
So this is really fun, I think. So the Germans definitely were not doing this. So the Japanese are so short of fuel, so they developed processes to develop aviation fuel from pine needles and pine root oil, birch bark, orange peel, camphor, tar, soya beans, sweet potato alcohol. So they did a lot of very, very clever scientific
Did
work.
this work?
So yeah,
Okay.
absolutely works. Yeah.
Well,
If you can make enough of it to conduct the war you want is another question, but yes, it absolutely works.
yeah.
So yeah, that's a brief summation of what I know about Japanese shortages.
Okay. Coming then to the final pre-submitted question here by Joe. What was the influence of British and US engines in Germany and the aero engine industry in the 20s and in the early 1930s?
So this is a pretty difficult one to answer briefly, but I'll try my best. So I'm going to use the papers of Bullman. So this is from 16th October 1937, after he's just got back from a visit to Germany. So he's been to investigate their engines. So this is just an essay he's written for the Air Ministry, which I think helps answer your question. So BMW and Siemens have basically been licensing American and British air-cooled engines to try and catch up, basically. So in terms of air-cooled stuff, the influence from America and Britain upon German design is quite high. And even if you look at lots of BMW 801 bits, it's pretty much the same as the Pratt & Whitney stuff that they first started building, just slightly changed. Whereas Daimler-Benz and Junkers really went for trying to really surpass the Merlin performance. I mean, this is what he's writing in 1937. So if we go to the next slide, please, Chris.
Done.
So yeah, so he's just saying here, BMW and Bramo, so there's air-cooled German radials. So he's saying that's a gallant attempt to copy the British and Americans. But he's saying the water-cooled inverted Daimler-Benz and Junkers, it's he's calling it virtuosity, a clean original design. So I think the German liquid-cooled engines are quite unique. They're very different. I don't see evidence of their being copied from allied designs from Britain or America at all. I think they were really quite clean sheet designs, which are really very different. So it's 50-50. So I think they copied our air cooled engines and they did their own thing on the liquid cooled engines. Why that is, I can't tell you. That's a question I can't answer at this moment in time. So I think,
That is
yeah,
all the pre-submitted
that's
questions.
that's all the
Yeah.
pre-submitted questions.
Okay, fantastic. Well, thank you very much, Calum, for answering those. We'll now open up the floor to all of you. Huguenot has already been collecting a lot of your questions. We have about a little bit more than half an hour to go, so we'll go through those as quick as we can. And of course, priority to those who are also sending those in via super chat. Just as a quick
Chris,
reminder,
Chris, can
yes,
I interrupt you?
of course.
So this is totally my fault because that's my PowerPoint I've made to answer the questions, and I've gone a little bit crazy with trying to make sure they're really good answers, and we've really used a lot more time than I thought we were going to be doing that. So, Chris, that's totally my fault. That's not your fault. So I'm happy to hang around for a little bit longer if you want to get through some of the questions that your people have submitted. So I know I said seven's the end, but if you want to go a little bit over, I'm happy to do that because we've run on, and that's down to me, not you. So
That's fine. Yeah, we'll see how fast we can go through those, and then we'll go from there if that works for you. Um, I just going to go quickly through the questions here. There might be a little hiccup on the stream as I go through the questions. But Cannon Fodder asks, how did the British react to the Axis engines and the aircraft improvements, or of the lack thereof? Thank you very much, Cannon Fodder, for also the support there over Super Thanks.
my impression from reading the files, so I've got so much of the stuff from Britain. It's almost a complete chronology, so you can start to see the trends. Some other nations like Italy, I don't have that much archive stuff, so I've only got spots, so I can't pick out the trends. But in Britain, I can. What's really obvious is that the first year of the war, we were really studying everything Germany did, really with great speed, you know. So if new German plane crashed, we would have the engine out and to Rolls-Royce in, a couple of days. The Focke-Wulf 190 report was all done very, very quickly. They did like a preliminary report to send out to the firms, and then they did very detailed report, which took months, and that went out to everyone. After about 1942, I think Britain realised Germany's got their own very unique problems. We didn't quite appreciate what they're dealing with the lack of materials, but I think we realised what Germany's doing from now on. This is not relevant to our own development path. So after 1942, the interest in Britain of what Germany was doing with engines kind of nosedived. And you'll see that. I mean, there are reports from the Royal Aircraft Establishment from like 1944 of German engines that are sort of 2 years old, and even in some of the reports at the end, someone's sort of saying, "Really, is this useful?" you know, and that's not an insult to Germany. It's because we sort of sensed that they were trying to deal with problems that weren't relevant to us.
Hmm.
So we didn't have shortages of all these alloys and materials. So, we didn't need to spend 2 years developing a new valve steel which didn't have nickel in it or something like that. That we couldn't use that information to improve our own technology. So that's just a very brief answer to the question.
Okay, thank you very much. Then the next question here from viewer Ole comes in. Where is the borderline between burning and detonating in a piston? Can radiation from a flame front detonate fuel ahead of ahead by radiation. So what starts as a flame front becomes detonations.
This is a very difficult one to answer. It's pretty difficult. You would be much better off speaking to an engine calibration guy who's sitting with the instruments looking at this data all day long. Because I'm a mechanical designer, so I have to design the bits that work. But I'm not a physicist or a chemist, and I don't look at this stuff. So essentially, I'm going to try and do something useful. I'm probably not going to completely answer your question, but I'm going to try and answer it in a way that might be useful for everyone else on the call. So, because this is a subject which is very, very confusing for everyone, even engine people, because it's very, very difficult. So, normal combustion is burning, and that is a progressive thing. So, the burning proceeds from a point you want, like the end of the spark plug, out to the edge of the combustion chamber, and it's controlled and predictable, and that's what you would like. So detonation is when that happens too fast, and pre-ignition is when that happens at the wrong time. So pre-ignition is it's ignited before you have sent the electricity down the ignition cable to spark the spark plug. So there would be a hot part in the combustion chamber, like an overheated valve or an overheated spark plug, that cooked the fuel off before you fired the spark. So that's pre-ignition, and that is lethal. You can burn a piston through in seconds, actually, if it's a very, very high performance engine, a few seconds. Detonation is a much more mild phenomenon in that there are engines which run their whole lives with detonation. Stuff like I think probably the Alfa Romeo T-Spark probably did that. So the Alfa Romeo T-Spark's got terrible combustion, so they put two spark plugs in it, and then they called it T-Spark and made it this sort of marketing thing. It's actually because it wouldn't pass the emissions tests without two spark plugs, but they turned it into some sort of high performance gizmo sort of thing. So basically, with detonation happening too fast, the reason it makes a sound that is called knock is because it's audible. It sounds like there's a hammer going, and it has a set. You can measure the speed, so it turns into a shock wave. So essentially, you need to have some conditions whereby everything is getting sufficiently hot in there that even though you've ignited it when you wanted it to start, it all goes too quickly. So there's probably several different ways it can happen, and even more complicated, there's an interplay between pre-ignition and detonation. So if you have detonation, that can help everything getting hotter and hotter and hotter, and then you can overheat the spark plug and you'll get pre-ignition. Or if you have a little bit of pre-ignition, that can then start off detonation because the whole thing's getting hot. So I'm not too sure about what the answer to your question is in terms of the radiation making the flame front start a bit further on. What I would suggest doing is, if you go onto my website, there's a contact form. Can you send me, try and word your question in more detail, and I will try and get back to you.
Okay. Then the next question here comes from Will. Why were the Germans married to the idea of driving the supercharger at 90 degrees? I've heard it was for packaging. What do you think? Seems like it really limited their ability to use two-stage superchargers.
It's all down to needing a cannon armament. So 1928 specifications. I've got a YouTube video on it where I read through the German document in German and translate it for you into English. There's like some bullet points in the specification document. So go and watch that video. But you had to have the supercharger on the side because the specification requirement mandated you needed a cannon armament provision through the prop shaft, which means you can't have a supercharger on the back. So
Fantastic. There we go.
that's basically it. Some of the German engineers make some additional justifications for it, such as you to get the air into the engine, it has to go through one less 90-degree bend than if you have the supercharger on the back, stuff like this. But the reason is the cannon through the prop shaft.
And then we just had Jack Ray coming in with a super thanks. Thank you very much, Jack. Did you note any differences in the way that the research programs were run? If so, did you see a difference in the quality and pace of results having a relation to that? So I assume comparing mainly, let's say, Britain and Germany.
Well, that's a really big question. It's very, very interesting. So that is probably a book. Seriously, that's like a book, or at the very least, of like a long essay. So I have been doing some research into that because I'm writing a paper on German Aeronautical Scientific Organization, which I'm hoping to get published, or I might just stick it on my website if I can't be bothered with getting it published. But it's not quite finished. So essentially, there are a lot of similarities because scientists are scientists everywhere, and before the war and now, scientists are just people. Everyone thinks they're special and so on because they sometimes wear white coats and things. So that's why do you think doctors wear white coats? Is because it's the mystique, and so that you go in and believe everything they tell you implicitly. So it's a mystique thing. So engineers and scientists are no different from that. Everyone likes the mystique, so they like to publish because they want to be famous. They want to be known. They want people to say, "Oh, Doctor So and So, he's the guy who published the thing with." That they all like that. I don't think many scientists are just sort of shy, retiring little boffins who are happy to sit and make studies and never be known for it. I don't think that's really true. I think they want lots of citations. It's these days you can't get funding for anything if you don't have a track record of publishing dozens of papers on it and get thousands of citations. You won't even get a job, you get sacked. So I think it wasn't quite that extreme then, but basically, even in the 1930s, British and German engineers were publishing almost everything they were doing in scientific journals. It's all being read. And the Germans kept publishing stuff until 1944 in academic journals. I kid you not. And these journals, Britain would get copies through like the Swedish embassy or whatever, Swiss embassy. They would just go and get the journals and send them to Britain. So almost until the end of the war. And so they said, "Oh, should we be publishing this?" But that's because that's how the scientists are thinking. They're not. A lot of them aren't even thinking about the war. It's like, this is my thing. I've got to get this published. People have to know I've done this. So in that respect, scientists are the same everywhere. So that's why it's so unusual to get one idea popping up somewhere and it's never been done anywhere else, because everything's being published all the time. So there's very little that anyone in any developed country knew that wasn't known in another developed country, because they all get the journals.
Okay.
So I think the differences are that I think in Germany they had a very big setup with the research being done in universities. So German technical universities then and now are they're pretty superlative. They're there aren't any that are better. And in America, you've got like maybe two that are better. MIT, Caltech, but in Germany they've got like 5 universities that are as good as those, but they're not quite as famous for whatever
They
reason.
don't work in English. That's
Yeah, so German technical universities at the time and now, but more so at the time, they were whole research institutes, but on their own merit. More than was in the case in Britain, which is mostly a funding question. It's not because British scientists were less smart or whatever. They probably had less funding, had much less facilities, A lot of these German technical universities had better facilities than the Royal Aircraft Establishment had, better wind tunnels and everything. So Germany did a lot of research at technical universities, Darmstadt, Dresden, there's half a dozen, Stuttgart. So the German research is a lot more concentrated in academic settings. These research institutes at the universities, and they've also built all these unlimited funding facilities like the Falkenrode, stuff like this, which otherwise known as the Hermann Goering Institute. So basically, German scientists just came along and the Nazis just said, how many things do you want? And they just said, I want all the things. And they said, okay. And they just went and built everything, So the research facilities there are just, unbelievable. The British, I've read the reports, British went and saw this stuff and they were just like, my God, this stuff, how did you lose the war? I mean, it's unbelievable. We've been, the engine test cell at Farnborough, the high altitude one, didn't really work for half the time. They didn't have a snow remover on it, so you feed in low temperature air to simulate the air if you're flying at 30,000 feet or whatever. Yeah. And it did stop working because you'd get the snow ice particles started forming. And the ice particles destroy the supercharger because the supercharger is spinning at 25,000 RPM and the snow particles go in and destroy it. Half the time it didn't work, and they went to look at the stuff that the Germans had at BMW high altitude plant, and they're just like, oh my God, this is unreal. So in Munich, the tram stopped working when they had the wind tunnel on.
Oh, for the electricity.
Yeah. It's like it was unreal. I mean, it's, so all that stuff is what kicked off Cranfield University in Britain. So Fedden went to Germany, saw all this stuff, and he's like, oh my God, this is unbelievable. He took as much as he could back home, and that's what started Cranfield University.
Oh wow, okay.
Yeah.
I have to write that down. That's a really cool piece of trivia there.
So, yeah. So Fedden created Cranfield, not just because he brought back the stuff. It was his brainchild, and Fedden wanted to improve British education and aeronautical research by combining the best aspects of German and American science. So we had a lot to learn from both the Americans and the Germans. So the British stuff was no less clever, but our facilities were really bad. We didn't have these amazing research establishments like you had all over Germany at the technical universities. And so we had to be very, very focused. And we made some mistakes, but broadly, if someone didn't say, I need this for this operational reason, it didn't happen. So we could only pick and choose very, very carefully what to research, whereas Germany could just do anything. And
which also has its negativities, I guess.
In so doing, they lost the war because 90% of it was of no military value, but that they started the space race because you had thousands of brilliant engineers given infinite funding.
Yeah.
And so at the end of the war, Germany had what I would call leftover research because they'd been doing all this stuff that was of no use for the war, but it was brilliant. So we couldn't start the space race off because we'd put almost all of our effort into militarily useful stuff. And we had nothing left to look into. We didn't have people looking into sort of, how do we get stuff into orbit,
So it wouldn't have helped you win the war, so you didn't look at it, right?
No. So broadly, the difference is our research was very, very focused. There's no difference in intelligence between the engineers in any of these countries, French, Italian, German, American. They're all very smart people, but they're given very different sorts of resources and targets, and also a lot of the German research, I think, was really spurred on by not getting conscripted and sent to the front.
Yeah.
So basically, you wanted to look busy from about from when the Russia campaign started to go bad. You wanted to look busy a lot. So basically, if you're, that's not just an idle fear thing as well. Thousands of German engineers and scientists were sent to the front. That actually happened. It's not just that they were worried it might happen. That actually happened.
Yeah.
And they tried to get them back later in the war. They would, oh God, we need these people. And of course, most of them were dead, but some of them were brought back. So some German servicemen were brought back from the Russian front because even the Nazis realised at a certain point, oh God, like the Daimler-Benz engine test cells in Stuttgart. One day the test cells stopped working, and some people were saying, well, "Why is no one running test cell 3?" And it's like, well, you conscripted Dietrich or whatever his name was. He's in Russia. That happened. I'm not.
Yeah. And then Dietrich they tried to get him back, right?
Yeah, they tried to get hundreds of them back to work on engine testing. So I've got the letters. So you can imagine you've got all these academics and clever people with almost unlimited funding and very good reasons to be busy. So it's not surprising they came up with all sorts of stuff which was of no use for the war, but was of immense scientific value after the war. So I hope that answers your question.
That's a fantastic answer there. And Jack also, who asked the question already in chat, said that he's very thankful for you to have given that great answer. Casey now, and this is an interesting one because it harks back a little bit to what we said in the beginning of the Q&A. How much more efficient could a World War II plane be if not designed for mass production? We don't mass produce F1 cars after all, or F1 car engines after all.
Yeah, I don't think I can dig it out for you live, because I'm actually at the family home. I'm not at my flat, so my 18-month-old son is ill, and I'm not there because I don't want to disturb him. He's supposed to be sleeping, so I'm up here.
We wish him all the best, of course.
Yeah, he'll be fine. They get well very, very quickly, but I don't have a lot of stuff around me. I'll see if I can send it to Chris this week, and maybe he can put out a tweet. So, Chris, can you maybe see if you can make a name so I can get this information over? So, I do have a graph from a German academic journal from about 1941, and it's a graph of, it's not absolutely what you wanted to know, it's a graph of engine power, and it's the difference in power charted across the years between the prototype engines and the mass-produced ones. So it shows you the difference.
Yeah.
I wish I could dig that up for you right now. I will send it to Chris.
Yes.
And he will send it to you. So off the top of my head, it's not a huge difference. It's something like 5%, if you averaged it, something like that. So I do have a little bit of data. I'll send it to Chris and he'll send it to you.
Yeah, so if I will post that then on Twitter. For those people who don't follow on Twitter, that is @MillAVHistory. I'll just post it in the chat. And actually, do you want to give your Twitter handle as well if people want to follow you?
Yeah, so I'm gonna.
We'll do a little bit of social media propaganda.
Yeah, I'm just looking at my own Twitter handle because I never.
Yeah, I always forget mine as well.
It's at Calum Douglas 1, so that's Calum with one L, CalumDouglas 1.
Hook, can you put that in the chat, please? Once you.
So I just realised that I can give one more slight answer to that. So
Okay.
When we were trying to prepare planes to shoot down V1 flying bombs, we had to just do everything possible to get the last couple of miles per hour out of the planes, because the V1s are about 400 miles an hour at 2,000 feet. And although a Spitfire 9 can do 400 miles an hour, it cannot do it at sea level because the air is really dense. So you need a crazy amount of power to do 400 miles per hour at sea level, even if a plane can do it at 20,000 feet. So we were doing everything. So we'd get Mustangs and Tempest and Spitfires, and they would polish. They would get the guys to strip all the paint off, polish the wings, smooth out the wrinkles in the panels, put filler in all the panel gaps, take the radio mast off, take all the bomb rack fittings off, everything you could possibly do to get the last few miles per hour out of it. So from memory, I think in a Mustang, it was about 18 miles per hour difference by doing a complete cleanup of the whole airframe.
Okay, that's good. That's a good performance increase. Yeah.
So, but the man hours, I mean, you couldn't mass produce that, right? But
Yeah.
so anyway, I hope that's a slight additional answer to your question.
Fantastic. Moving on to, I'm not quite sure if I can use this name online, but your name starts not. So, not, I may have missed this in the book, but given how Rolls-Royce did actively decide against a fluid supercharger coupling due to time constraint, how did Bell or Allison manage to get it working so quickly? And because not you have given me the hint to the book, we are of course once again just quick reminder everyone talking about the Secret Horsepower Race, which Calum Douglas has written. And if you want to have this book or any other book that is published by the publisher Mortons for a discounted price, use the discount code that is provided on screen, MA10, and order directly from their website. And generally speaking, just a little hint here to all the viewers, if you order directly from the publishers instead of through Amazon, the author actually gets a higher cut and their work should be rewarded. Because how long have you, this is the second question, but how long have you worked on this book?
That took 6 years to
There
write.
we go. So reward Callum for his work because he has really written the treasure trove here on this topic. Secret horsepower race, absolutely. Do you want me to repeat the question, perhaps?
Sure, go for it.
So the question was, why not? How did Rolls-Royce actively decide against a fluid supercharger coupling due to time constraints? Because of this, how did Bell and Allison manage to get it working so quickly?
I think we could have eventually got it working, but you've got to remember that we had less resources. So going back to what I was saying about how we did R&D, by the time you had a Spitfire 9 with two-stage, two-speed supercharger, the results from that are ahead of anything the Germans come up with until the UMO 213E or the DB603L, which I don't think ever saw any active combat or mass production at the end of well, it's right at the end of the war. So if you're at Rolls-Royce and you go and speak to, the Aeronautical Research Committee or the Air Ministry and say, I want another 20 engineers and £50,000 to do a fluid drive coupling for the supercharger, and they say, well, what's the performance gain? At that point, they would probably say, well, it'll take us 6 months and we'll have to stop, we'll lose production of 2,000 Merlin 61 engines while we're retooling it. They would have, it probably have been laughed out of the room, kicked down the stairs. So we didn't have the resources to do it. And I don't think there was a performance advantage there for us by the time we'd got to that point. The Americans were very interested in it. I'm not sure they did it that quickly, because the Americans studied the DB601 right at the start of the war. Because when we captured stuff, we would send it to America. So there's a slight delay because you've got to ship stuff or fly it over. And they had problems because people used to steal stuff off the engines in transit. So they would they would send a guy to watch the engine. And there's a report. The guy says, we've lost, I think, a BMW 801 turned up without the part of the supercharger controls. And it says in the report, it's vanished in transit as usual, despite having, private so-and-so to watch. So
This reminds me of the first Zero that potentially could have been tested by the Allies, which crash landed, and they put a guard on it, and then a bunch of Australians just ripped it apart for souvenirs. It happens. This is what happens.
yeah.
Yeah.
So nevertheless, I think it's mid 1941. So there's a Society of Automotive Engineers conference in America, and they present a study of Daimler-Benz engine and the supercharger coupling. So there's quite a big study on it. So the Americans knew exactly what had been going on with that since mid 1941. So I don't have the archive papers to show what happens after that, but they had enough resources by the time America entered the war that I think if they wanted to have a team of people just doing that, they would have just done it. You look at all the hyper engines that Americans did. You know, they had enough resources to waste hundreds of engineers making all these crazy engines, which were absolutely no use to anyone, like the Tornado and the Chrysler hyper engine. I think there's about four in total, and they're all complete waste of time. But they had enough resources to do this kind of stuff, so I think it's no problem for the Americans once they decide they're interested in something.
They'll just go and do it and
they'll
overkill
just go
it.
and do it.
Yeah.
Yeah.
Okay, then the next question here comes from Luke. And remember, chat, you can still continue sending in questions. We have a bunch here. Will be, let's say, another 15 to 20 minutes online. But these questions are not getting lost in the ether afterwards either. We may, perhaps, Calum, if you're up for it, repeat this again in the future as well. So Luke asks, how did engineers deal with the problems of added heat as engines become more powerful? And I think this harks back a little bit to that discussion we had earlier about radiator size and high pressure in radiators.
So there's probably three answers to this. So one is the obvious one, which is you put bigger radiators on stuff. So if you go and look at, despite the fact that we had a pretty good cooling system, if you go and look at a Mark 1 Spitfire, preferably in a museum, but you can Google it, then Google a Mark 22 or Mark 21 Spitfire with Griffin engine, and you look at, I mean, the difference in the radiator size is unbelievable. I mean, it's twin radiators, and they're, the openings are huge, which is really because the Spitfire was really pretty much beyond its development point there, and they couldn't fit the radiators further up into the wing. You can't extend the duct forward because the wheel well opening's there. So you've just got this huge radiator, so the duct inlet is just this like massive hole. So that is one answer to it, is you just put huge radiators on stuff. But it's a really bad solution to do that. So aerodynamic drag goes up with the square of the speed, but the power required to overcome aerodynamic drag goes up with the cube of the speed. So you really do not want to put drag on a plane, because to make the performance difference up, the engine power needs to be cubed in relation to make up the difference. So it's a really big, it's not just the V squared, it's the power is cubed. So it's a really serious problem. So if you want to go twice as fast, you need 6 times the power. So it's sorry, 8.
Yeah. My math was failing me there. Yeah.
Yeah. So it's
Oh, that puts it in relation, doesn't it? I mean, perspective. Yeah.
so it's yeah, it's pretty serious. So the second way you can do it is improve the heat transfer. So Germans did all sorts of crazy tests with different fluids, trying to make they made all these synthetic things and stuff like this, and they found what everyone had known before, which is that water is the best heat transfer fluid you can use. The only time you might deviate from that is if you're running a nuclear reactor, and then you might want to use sodium or something like that. But that's a whole different ball game. So we do not do that in engines. So water's the best thing you can use, but it boils. So we need to have very, very high pressures to stop it boiling. So the ideal solution is you need to, if you look at water pressure and the water temperature throughout the war, in Britain they're just going up and up and up and up. So at the end of the war, it's about 4 atmospheres of pressure in the cooling system and 135 degrees coolant temperature. So in Germany, both those numbers are a lot less, and then you get a much more efficient heat transfer, so you can get a lot of the engine heat out without putting a bigger radiator on it. So the third way you can do it is chemical cooling. So if you use methanol water or nitrous oxide, there's a lot of cooling that happens inside the supercharger in the engine, which cools everything down. So if you increase the engine power with water methanol, you can, for example, I've got some American test reports. I think you can basically double the engine power and only put about 10% more heat into the engine.
Oh wow, okay. That's a staggering increase then, yeah.
Yeah. So yeah, you can go really crazy with water injection. So if you want to go really mad with it, so the water flow rate exceeds the fuel flow rate. So
Okay.
seriously, so if and this isn't a test setting, I'm not saying that was used in operation in World War II. I'm saying that from the point of view of if you want to go really crazy with it, to get maximum power, there's more water going in than fuel. So that's absolutely mad.
Okay.
But that happens, and so the methanol cools down as well. Although the methanol is mostly used as antifreeze. That's the main reason it's there, is because you can't put pure water in the fuel the water injection tank, because you fly up to about 10,000 feet in the aircraft and it's all frozen solid. So it's mostly in there as an antifreeze. So the chemical cooling. So those are the three solutions. Bigger radiators, which is pretty hard to do because it's very hard to package. So that's a big problem for Messerschmitt. Early Messerschmitts don't even have radiators under the wings. It's just a nose radiator. It was never designed with radiators under the wings, but it's very hard to package bigger radiators. So big radiators, or increase the pressure and the temperature of the coolant, or chemical cooling. So those are your
Those are the
options.
options. Excuse me. Barton then asks if we compare the main belligerents. Well, he's actually going with the UK, the US, Germany, and Italy here. So let's stick with those. Who had the best mass production of piston aero engines? His guess is the US due to the use of advanced measuring devices. Now, I guess it depends on how we qualify the best, but I guess output terms of manpower hours, perhaps.
It's really tough. I'll give you three bests, so I'll try and pick out the best bits that we all individually did. I
Right.
think best is very difficult to isolate. Um, the Americans just did an unbelievable job mass producing so many of their engines, and the Americans. This is a really annoying one. I'm going to come back to the stuff about mass produced Packards and Merlin engines. So there's this story that drives me crazy, that Merlins were hand built and Packard mass produced them, which is complete nonsense, by the way. But it was probably true up to about 1935, and then so. How do I avoid going down this rabbit hole? Okay, we're gonna go down the rabbit hole. We're gonna go down the rabbit hole. I'm
Enough.
sorry. We're gonna do the rabbit hole. So no one has ever written anything about this since, I think, about 1950 something. There's one textbook on it, and there's like one paper, which is a US. It's like a US Department of Defense thesis paper, which is very, very good. I'll send Chris the link because it's really important. So no one knows anything about this, because I think to know about it spoils our idea of what Britain was supposed to be in the war. So our national idea of what Britain is supposed to be in the war is the underdog nation of poor, downtrodden Brits who were defending themselves alone against the Nazis until the Americans came in, and we had no resources, and we almost lost, and all this kind of thing. And we had these genius boffins like Barnes Wallis and R.J. Mitchell and so on, who saved us from catastrophe and so on. Some of that is true, but I think the history has been perverted because that's the story that we are supposed to have. And the whole country's covered in Spitfires, and there's this. I do like Spitfires, okay, but this drives me mad. What Chris? What was this thing? There's going to be like a Spitfire, a huge stainless steel Spitfire sculpture made, costing sort of millions of pounds.
Yes, I've heard about this, but I don't know the details.
Yeah, I think it's being sponsored by Airfix or something like that.
Okay.
And so yeah, it's all linked into that. So we've got to have the Spitfires that if we didn't have those, we had nothing else, and we would all have all this kind of thing. You get the idea. And I have a somewhat different view on it after having read archive files for 6 years and more, because I keep reading them. Just because I've published the book, I don't stop reading them. I know a lot more than when I started writing the book. So no one has written anything about the Committee of Imperial Defence, and you should do, because it's the Committee of Imperial Defence is the kind of British defence deep state. So it was basically first brought in during the Boer War, because the Boer War was not going very well, and the British establishment, even they realised this isn't going very well. We need to do something here. So they created the Committee of Imperial Defence, and it's basically a think tank of all the top pertinent people who meet up, probably in a little dark, smoky room in secret, and actually work out what you should be doing. And they were given not necessarily a budget to go and do things, but they were given, I think, a lot of leeway in the advice that was given and what Parliament would decide to do. So I think the committee would give advice to Parliament, probably informally, and the official parliamentary committees would then say, "Oh, I've come up with a great idea. Why don't we do this?" It's actually because this committee who was formed by people who know what they're doing, had come up with it and told them what to do. So the Committee of Imperial Defence basically war-gamed World War II in, I think, 1928. I say war-gamed in as much as you can war-game something in 1928. Yeah. It's not CGI, but they did that. And basically by 1930, they'd laid down plans for how Britain should defeat an enemy in the next European war. By 1935, they had a complete plan in place for transforming the entire British auto industry to aviation defence manufacture. So we had shadow factory scheme. We started producing Bristol engines, I think. I shouldn't go from memory here. I think the first one was made in something like 1936. So years before the war started, we had everything prepped to switch over to mass producing military materials at the drop of a hat, new factories built, everything. And all of this was basically planned at the top level by the Committee of Imperial Defence, who is this kind of shadowy group of politicians and aviation experts and defence people. So the American essay, the American Department of Defence, I think, sponsored a PhD or a master's thesis. So there's a very good American contemporary, I mean, just from a few years ago, 10 years ago or something. And it's basically saying that the American Department of Defence should try to adopt a lot of the lessons from how you run a defence structure with something like the Committee of Imperial Defence. So they thought it was a very, very effective system for how you organise a country. Essentially, that notion of the sort of bumbling British approach to things is it's not correct. I've gone so far down the rabbit hole that I do is probably not assisted by this glass of wine which I've just finished. Chris, can you repeat the original question?
Yes,
So,
so who had the best mass production of piston aero engines?
yeah. So, the British had organised this mass production in the mid 30s, and I've got it in documents. So we did tests with the Bristol Aero, the Hercules, made in I think 3 different plants. So some by Bristol and some by 2 of the other car factories, which had been turned into aero engine factories. And they found all the parts were interchangeable from one to the next. They had to be. It says this in the report. Or everything has to be interchangeable, otherwise you can't run a war. Because there's no way you're going to have one box of spare parts from the aero engine plant in Bristol and one box of spare parts for the same engine that was made by, a subcontractor down the road. You'd never, ever be able to succeed in a war. So you can't do it. So really, by 1940, all of our production stuff was standardized, and everything was interchangeable, and it had to be. There's a parts manual at Q Archives, which is a list of all the part numbers of the Packard Merlin and the Merlin, and it's an interchange, right? So it's got the Packard part number and the Rolls-Royce part number, and it says, oh, if I've got that one, what's the Rolls-Royce part number? And the reason you have that is that if you've got an engine in the field and you don't have a Packard spares box, but you've got some Merlin spares, you have to know what the cross-reference is to use the Merlin spare part. It doesn't apply to every bit of the engine because the Packard had their own supercharger drive, right, which is different, and they got American ancillaries. But all the rest of the bits of the engine, more or less, you can use Merlin spare parts. So the tolerances all had to be the same. You can't have these mad different. It beggars belief that people have ever believed that you could have run a war on that footing. So credit is given to the right country, but for the wrong reasons. So we've given the Americans, well, I say we, many people give the Americans credit for mass producing the Packard when the Merlin was all hand built, which is rubbish. So that's complete junk. So what really happened? So the Americans, we do have the Americans to thank for it, but not for that reason. So the reason Britain could mass produce aero engines, which we were doing at Rolls-Royce Glasgow with completely unskilled workers before Packard ever made an engine, was because of American automatic machine tools. So Americans made the best manufacturing tools. So they were even used by the Germans. The Germans had real problems in the war because they had loads of their machines were American.
Okay.
And they couldn't get them anymore. And the only people who were making ones which were maybe as good were I think the Swiss. And I think they couldn't get nearly enough of them because I don't think the Swiss are manufacturing machines in the scale that the Americans are doing. So essentially, British mass production of aero engines was facilitated by using American machine tools, which all had to be shipped across the Atlantic. So yes, we have the Americans to thank for it, but not for the reasons that we think they deserve the thanks for it. So that's not to say the Americans didn't do anything differently, because the British thing had to be developed using what we had, which is we're going to use these car factories to manufacture aero engines. We're going to use all these subcontractors who've never seen an engine before. We're going to build a few factories here. And like the Ford factory, the famous Ford factory that everyone talks about from this, the stupid remark in Stanley Hooker's book when he's talking about the guy from Ford saying, "Oh, we can't make these because the tolerances are all blah 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 blah." So the Ford factory, it's a Ford stamp on the factory. They administrated it. The Air Ministry built that factory.
Okay. So it was just under the supervision, or
yeah. Ford didn't
Okay.
build that factory.
Huh.
Ford were brought in to administrate it. So they didn't pay for it or build it. It's not a Ford factory. It's an Air Ministry factory, but the Air Ministry doesn't have hundreds of production people to administer the workings of a factory. So Ford agreed to take over the running of it. That's the basis on which it was done.
Okay.
So it's I hope that begins to clarify things a little bit about what was really happening here. So
I think if we can leave the question just there, just so we can go through
yeah,
a couple of
yeah,
more.
absolutely.
We also had another super thanks coming in. Thank you very much, Cannon Fodder. Now, this is a fun speculative question. How much better would all these engines that were produced during World War II just have been if they had been designed with access to computer aided design programs? I mean, it's speculative, so I don't think we're going to nail you down for an answer here, but
Um, that's really difficult because I have to know if you're trying to imagine that we're going to have some sort of alternative history thing where we have World War II now, and you make the engines now with all of the other stuff we've got, or if you're just talking about going back with a time machine with some computers. I'm going to go for option two, being what you're asking. So if I got a whole load of computers and take them back to 1930 and give them to Rolls-Royce, what would have happened? They would have been designed a lot quicker, and they would have made less mistakes. I using with the other constraints they had, I don't think the performance would have been that different. It would have been a bit better, but I don't think people appreciate how clever these people were. You know, we have computers now, but honestly, if you don't know if you don't know the fundamentals, you're just going to design junk anyway, and you wouldn't believe in companies the amount of computation time that's wasted. People doing simulations of designs which are obviously stupid. The waste. They run these optimization routines. They've got AI tools and stuff, so you can say, I've got a problem. I need to do a thing from here to here. It can be this big here and that big here. I've got a bit through the middle, and it like morphs the shape iterations into the ideal thing. But you still have to put some constraints in there, right? So you can have you can pick a stupid scenario to get it to perfect. So you can get an absolutely perfect stupid thing out of your simulation and think, oh, I've got a perfect stupid thing. This is the best thing in the world. Whereas if you get someone with a pencil who actually knows what he's doing, he said that's a completely stupid way of doing this in the first place. And these guys, the really good ones, they were geniuses. They were absolute geniuses. And guys like Ullman in Germany, who worked for AVL List. It became AVL later on. He was like hand calculating the gas flows in and out of the engine and the cylinders with different valve sizes and port shapes. And so it would have been a bit of an improvement, but I think most people don't appreciate how clever these people were, and so I think the improvement would be less than you might imagine, unless you remove them from World War II and bring them to today's world, where you've got all the advances of the machine tools and all the rest of it and so on. So I'll end this question with an interesting one, which is a point I always make to people. They say, "Oh, you're romanticizing the past and so on, and we're all very clever now." And I say, "Really, are we?" Well, I'll tell you for sure. If I went back to 1935 to the Rolls-Royce design office, I would be the T-boy. I would be the T-boy if I was lucky. Maybe I'd get to be a trainee draftsman. If you get any one of these really good guys, even from 1920, and you take them to today, they would be flying in a couple of weeks, because the mathematics these guys had, because they didn't have any computers, they all had to be done with mathematics, and all the important branches of mathematics were all known then,
Yeah.
Um,
Well, if you would have been the trainee
So
back then, I think
I would have been a trainee, and they would have picked up computer. They would have learned to code in about a week, because coding is just it's just maths in stupid people language. It's maths turned into words so that you can kind of understand it a bit. So they would have learned to code, and they would have just taken to it like a duck to water. Whereas if you take today's engineer back then, you'd be useless.
okay.
Couldn't do anything. Wouldn't be able to machine. Probably couldn't do a drawing with a pencil properly. Uh, So I like to look at it in those terms when people talk to me about getting rosy-eyed about the past. That's not how I look at it.
Okay. For the last couple of sets of questions, shall we just do quick fires so we can get through as
Yep.
many as possible in the next 10 minutes?
Yep.
Kai asks, how important, and this is a cool one, I think, important were the Supermarine S5 and the S6 for British fighter development? So those are the racers, of course, built by Supermarine for the chat.
It's all really important. S5 and S6, I think, it's obviously very, very important for Supermarine. I think a lot of it's also important for. It's important. I think you've got to remember, the success of the Spitfire is a lot more than just R.J. Mitchell. So when Beverly Shenstone, the Canadian aerodynamicist who actually did most of the aerodynamic design of the Spitfire, came to work in Britain, he went around several different companies trying to get a job. He didn't come from Canada to go and work for Mitchell. So he came to Britain to try and, because there wasn't much going on in Canada, right? So eventually he went to Supermarine because he was turned down from, I think, his first interview, which wasn't even Supermarine. He went to Supermarine, got a job in Mitchell. If Supermarine hadn't had the cachet of having won those Schneider Trophy races, do you even think Shenstone would have gone there for a job? Maybe. He might not even known who Supermarine were, because Supermarine mostly made flying boats, right?
Yeah.
So, yeah, all this stuff about monoplanes and all the rest of it is all very important. But I'd like to emphasise that without the cachet of those wins, if you can't get good people, you're not going to be able to make, something like a Spitfire. You need dozens of very good people to do that. It's all very well having one guy like Mitchell to push a vision, but you need a lot of very, very good people. And if you don't have company cachet, you're not going to get them. So I would say, at least as important as the science is the kudos. And would they have got Shenstone without it? I don't know. Maybe not.
Okay, then next question here, quick fire. Yada, was there any information sharing about between alliances, i.e. British and American Intel for engine developments? Was there? I think we can say yes.
Yes, it was a little bit one-sided at times. They didn't want to send us turbochargers for quite a while. They were very secretive about that. So it was a little bit one-sided. I'd say it's mostly information from us to them. But we were getting so much material reward, lend-lease, etc., that I don't think we were in a position to complain.
Okay, and then the last question here, Darius, where can we go to learn, read, and listen more about this subject? And I think the answer is obvious. That would be your book. But do you have any other recommendations for this?
Yeah, so the Rolls-Royce Heritage Trust books are all worth having on the various Rolls-Royce engines. There's so many books written about the Merlin. Honestly, they're almost all worthless. Seriously, they don't buy them. Get the Rolls-Royce Heritage Trust ones. They're quite small pamphlets. They're not complete, right? There's a lot of detail left out, but they're very, very good and they're actually correct. Whereas there's so many books about the Merlin, and most of the people who've written them haven't even been to the Rolls-Royce archive.
Okay.
They just don't. The go and subscribe to the Aircraft Engine Historical Society. So that's an amateur group in America. It's just run by a few old guys who are volunteers in America, and they've got a website which, if once you figure out how to navigate it, has got a huge amount of stuff. So if you join as a member, you get additional stuff. You can see all the conference reports. They have got stuff like they've got presentations there from Pete Law on the SL-71 engines. So Pete Law is a member of the Aircraft Engine Historical Society. So you can go and read Pete Law's presentation on the SL-71 if you remember. Loads of World War II stuff. So go and do that. Get the Rolls-Royce Heritage books.
And then your book, I would say, and I just want to plug this again. Also, thank you very much for the cooperation with Mortons with the 10% discount for all of you in the chat. Calum, I think we should say we will cut it here for today.
Yeah,
2.5 hours.
there's just one point I'll like to make.
Sure.
Some of the beady-eyed among you will possibly look at the 10% discount offer from Mortons and then someone will say to you, oh, I bought it from Amazon at 30% discount. And that's true. You can absolutely go and buy this from Amazon, 30% discount tomorrow without using this code. And that's fine. You can do that. But to let you know, the amount of money I get if you buy it from Amazon is, it's a very, very small amount of money because the royalties I get, they are net. Okay, it's not gross. So when Amazon does a discount, they're going back really close to the price they paid for the book, and they don't care because they just want they want to dominate the market. Yeah. So that 30% discount, that's my money. So if you go and buy it from Amazon at 30% discount, I seriously get virtually zero. So yes, it may seem to you ridiculous. Why am I getting a 10% discount for something I can get a 30% discount any day of the week? And the answer is because
it's the author's. Author's cut is minuscule in Amazon.
It pays the author. And when I say it took 6 years to write, I mean, I actually spent 6 years on that.
Yeah.
I probably spent £20,000 just on travel for archives. And if I add up my time, I think it cost me about £100,000 to write that book. So seriously, that's the reason to use the discount and not just go and save money on Amazon. So unless you are using a food bank, please use the Mortons order and don't buy from Amazon. Thank you.
Yeah, definitely. And I will add to what Calum says is absolutely true. The Amazon always takes away the author's cut and leaves basically nothing. And with the amount of information that is in this book, it is an absolute bargain price at Morton's with the 10% discount as well. And the 10% discount also works on all the other books, so you can bulk order something and get a nice discount there as well. Calum, thank you very much for answering all the questions. Thank you to the chat, who has been absolutely spectacular with the contributions. Roughly 200 people were here all the time, which is really cool turning out. So thank you very much. Thank you, Calum. And we'll reconvene hopefully sometime in the future.
Cool. Thank you very much, Chris.
And we are